we present midpoint interpolation to run compact and separated representations for few-shot class incremental learning called MICs. I'm Solang Kim from Ulsan National Institute of Science and Technology from South Korea. When learning models are trained in a streaming data situation, they often face catastrophic forgetting. Catastrophic forgetting is a phenomenon where learning new knowledge causes the model to forget previous learned knowledge. As in the image, when there's a change in the data distribution, the model tends to overfit to the new data, resulting in the forgetting of previous knowledge. Continual learning aims to address the catastrophic forgetting problem. In this context, we focus on the task of a few-shot class incremental learning, which not only prevent catastrophic forgetting but also enable the learning of new tasks using only a few samples. Few-shot class incremental learning typically involves two stages, the base session and the incremental session. In the base session, the model is trained to classify a comprehensive set of base classes using a relatively large dataset to establish foundation knowledge. During the incremental session, the model is trained on new novel classes with a limited number of data samples. This stage aims to enhance the model's classification capability while preventing forgetting the knowledge of previously learned classes. Early research in few-shot class incremental learning focus on strategy for the incremental stage with a focus on preventing the forgetting of base classes. This involved various methods such as graph-based memorization in topic, classifier refinement in CEC, and parameter space theories in FSLL. They were mainly methods on how to run novel classes given as few samples. However, non-parametric methods of freezing feature extractor and classifier into prototype have been shown to be more effective than these algorithms. This discovery shifted the research focus toward optimizing the base sessions. Recent works have shown the effective training on base session might be more impactful. They use mix-up augmentation in base session, treating mix-up as auxiliary classes to reserve space for future novel classes. It helps minimize intra-class variance and maximize inter-class separation, leaving more space in the feature space for novel classes. Specifically, FACT assign feature mix-up of base classes to the closed virtual classes. Alice generates samples of virtual classes with input space mix-up. However, this approach utilizes hard labeled samples composed of 0 or 1 for virtual classes, which means they do not smoothly assign labels. Additionally, for virtual classifier corresponding to mix-up samples, they use randomly initialized learnable weights. Furthermore, these methods generally rely on a frozen representation. This limitation restricts their effectiveness in learning new features from novel classes in incremental stage. Our study deviates from the limitation of previous research. Earlier study mainly focused on either the incremental or base session. So they either struggled to apply new feature or tended to forget previous knowledge. To address this, we consider how both sessions could be effectively managed for learning. Our proposed method operates with a unified learning strategy for both sessions, ensuring efficient learning of new knowledge while preserving existing knowledge. Furthermore, previous approaches did not smoothly assign labels. To overcome this, we introduced a virtual classes and a soft label polish for mixed samples. Additionally, for classifying a virtual class, we propose suitable location for a virtual classifier. MICs generate mix-up samples by blending features from different classes. This involves selecting pairs of samples from distinct classes and then merging their features to create a mix-up sample. This blending is achieved using the manifold mix-up approach, which combines features at the hidden layer of the model. In this process, the mix-up ratio denoted as lambda determines the portion of each sample in the mix-up. Then the method computes the sublevel of each mix-up sample. This subleveling considers how much the mix-up sample is similar to virtual or original classes. The class probability for a mix-up sample are adjusted based on the lambda. When the mix-up is approximately half and half of the two images, the probability assigned to the virtual class is set high, while the probability for the original class are set low. Conversely, when lambda is near 0 or 1, indicating a mix-up sample that is very close to one of the original classes, the virtual class probability is low and the original class probability are high. The process adopts an additional parameter gamma, which determines the steepness of the decrease on original class probability as lambda approaches 0.5. Also, as shown in figure, Mike's introduced virtual classifier at the midpoint of base classifiers. However, prior works introduced an extra runnable classifier for the virtual class, which is not in the middle ground of the original classes. That enables Mike's to directly embed mix-up samples at the midpoint classifier to enlarge the in-between space. Training phase of Mike's target both base and incremental training stages, and the running process is the same in both stages. Mike's updates a subset of the feature extractor's parameters with a lower absolute value to relieve forgetting. This subset is denoting as zeta epsilon, where epsilon represents the subset of parameters with lower absolute values. An epsilon value of 0 indicates the Mike's frees the feature extractor. During the base session, we set epsilon to 1, while in the incremental session, epsilon is set to a value smaller than 1. The experiment setting following topic, and the benchmark used are Cypher 100, MiniMageNet, and CUV dataset. The experimental result across all three benchmarks demonstrate a consistent pattern. As each session progresses, both accuracy and the performance dropping rate show outstanding results compared to other studies. Additionally, our method is theoretically guaranteed to enlarge the thickness of the margin space between different classes. A larger value of thickness indicates a larger margin space between classes. Our method achieves a larger normalized boundary thickness than mixer-based prior works. It leads to essentially enhance the margin space between classes. Additionally, we propose the normalized variance to analyze importance of this intra-class compactness and inter-class separability of representation. The smaller n-var means the better representation. In the effectiveness of components of mics, we can observe that mics demonstrate the highest accuracy and the smallest normalized variance in the last session. Here we compare mics to the extended Alice and Clum. We extended the learning strategy during base training to the incremental sessions, when extending existing approaches to reserve margin space for incremental learning. There is significant forgetting. However, despite these challenges, mics demonstrate that these approaches can still maintain consistent performance during the incremental session. We visualize the representation of mics by evaluating the TSNE plot of the feature vectors. Mics clearly show more interclass compact and interclass separated representation. In summary, we introduce mics, a novel approach in few-shot class incremental learning that emphasizes intra-class compactness and interclass separability. We discuss how mics innovates with mix-up sample construction and midpoint classifiers, and how it outperforms existing methods in few-shot class incremental learning benchmarks, backed by a theoretical framework that enhances the representation space and boundary thickness. Thank you for your attention.